All right, so what we're going to do in this video is we are going to prove something. We're going to show that when you do a reflection of a geometric figure like a triangle, then the reflection is actually congruent to the original, okay? So here we have GHJ has vertices at 3, -2, or at 4, H is at 4, -9, and J is at 7, -5. Okay. Then it says triangle KLM is a reflection over the x-axis of, I should have put on here, of triangle GHJ. Sorry about that. Okay. It's a reflection of triangle GHJ over the x-axis. And then it says show that the reflection is congruent to triangle GHJ, okay? So here's what we need to do first. We need to identify the vertices of K, L, and M based on G, H, and J. So K is going to be at, remember when we do a reflection over the x-axis, what we do is we keep the x value, but we change the y value. We change the sign of the y value. So if G is at 3, -2, then K is going to be at 3, +2. Then H is at 4, -9, so L is going to be at 4, +9, and then J is at 7, -5, so then M is going to be at 7, +5, okay? So this is another triangle that's reflected over, it's a reflection over the x-axis of triangle GHT. So what we're going to need is we're going to need the measure of GH, we're going to need the measure of HJ, we're going to need the measure of GJ. Okay, I forgot to put the segment symbol here. Segment GJ. Okay. Then we're going to need the measure of KL. Then we're going to need the measure of LM. And then we're going to need the measure of KM. Okay. And then we're going to use the distance formula. So GH, the distance on GH is going to be, well, so this is going to be the square root of, all right, so the x value on G is 3, the x value on H is 4. Those are 1 unit apart. And so that's going to be 1 squared plus. Then we have -2 and -9 for the y values. Well, -2 is 7 units away from -9. And so that's going to be 7 squared. And so that's going to be the square root of 1 squared is 1 plus 7 squared is 49. And so that's going to be the square root of 50. So the measure of segment GH is the square root of 50. Okay. Now we're going to need HJ. So the distance there is going to be the square root of HJ. We're going from the x is 4 and 7. So the distance between 4 and 7 is 3. So we're going to do 3 squared plus. Then the y value is -9 and -5. Well, -9 and -5 are 4 units apart. So that's 4 squared. So that's going to be, that's going to be the square root of 3 squared is 9, 4 squared is 16, and so that's going to be the square root of 25, okay? So square root of 25. Now we're going to need GJ is going to be the square root of, okay, G to J, we're going from 3 to 7. So the difference between 3 and 7 is 4, so that's 4 squared plus, and then we're going from -2 to -5. The distance there is also 3. Oh, this looks like we've got an isosceles triangle here. And so that's going to be the square root of 16 plus 9. 16 plus 9, which is the square root of 25. So square root of 25. Now I know that the square root of 25 is 5, but here's the thing. In our procedure, we're trying to compare radicals here, so I don't want to turn these into 5s. I want to be able to compare the square root of 25 to the square root of 50. So I'm going to leave it as the square root of 25. Okay. All right, so these are our measures. So we have a longest side, which is square root of 50, but the other two sides, the medium and the short, are both the same distance. So we'll just call, we'll call them both, well, we'll call one of them medium and one of them short, okay? Now let's do these measures down here. All right, so let's do KL. So the distance is going to be the square root of, so from K to L, our x's go from 3 to 4, and that's 1 squared, plus 2, y value is 2, to y value 9. The distance between 2 and 9 is 7, so that's 7 squared. So that's going to be the square root of 1 plus 49, which is the square root of 50. Okay, so far so good. Remember, we want to show that it's that these two triangles are congruent. And so we're going to use the side theorem. All right, so now let's do LM. So the distance on that one, L to M here, we're going to go from 4, x value of 4 to x value of 7. There's 3 units between 4 and 7, so that's 3 squared, plus. Then between 9 and 5, that's a distance of 4. So that's going to be the square root of 3 squared is 9, plus 4 squared is 16. And so we have the square root of 25. And that's what we were hoping to get, square root of 25. And now Km will go from 3, 2 up to 7, 5. So distance is going to be the square root of, from 3 up to 7, that's a distance of 4. So we're going to go 4 squared, plus from 2 up to 5, that's a distance of 3, 3 squared. And so that's going to be the square root of 4 squared is 16, plus 3 squared is 9. And so that's the square root. 16 plus 9 is 25. And sure enough, we got another square root of 25. And so our longest side is square root of 50. And then the other two sides are both square root of 25. So we'll call one of them the medium size and one of them the shorter side. And sure enough, our longest sides have equal measure. Our medium sides have equal measure. And our shortest sides have equal measure. And therefore, triangle GHJ is congruent to its reflection. It's just a reflection, KLM. And this, the reason we're doing this is we're proving, because when we learned about reflections, we said that it makes an exact copy of the triangle, but reflected over one of the axes. And this is proof that the reflection is congruent to the original triangle. Now, you can actually do this same thing for rotations. So if we made KLM a rotation over the, or let's say about the origin by 90 degrees clockwise of GHJ, the rotation would also be congruent. If we did a translation, it would also be congruent. And I'll remind you that that's what makes it a rigid transformation, is the fact that the triangle, the new triangle, is an exact copy. It is congruent. Okay, so I just wanted to do an example to prove to you that reflections of geometric figures are congruent to the original geometric figure.